Son olarak karşıda çok işleydi. Dedik, A şartını falan uzandırıcı hüküm seviyeye da bir hata var. Hüküm seviyeler. Sen ne diyorsun?
Yok, funksiya. Funksiya ataladi. Funksiyani ataladi deyish bu ham şey var. Kitobni o'qilmaydi. Kitob o'qiladi. Kitobni o'qiladi deyish noto'g'ri. Kitob o'qiladi. Kitobni o'qiydilar. Kitobni o'qi. Kitobni o'qidi. Kitob o'qildi. Xat yozildi. Ma'ruza qilindi. Gani qo'yish ham noto'g'ri, nini qo'yish ham. Çünkü gapni egasi. Gapni egasi. Nima? Kim degan savolga javob beradi. Bizlere juda boy, shunaqa niyatim bor, Alloh nasib qilsa, ona tilim boyligi degan kitob yozish. Mana qarang. Yuvdi degan so'z. Yuvildi degan so'z bor. Qo'lni yuvdi. Qo'l yuvildi. Yuvindi degan so'z. Yuvishdi degan so'z ikkita ma'noga. Masalan, bitta ishni birga bajarsa ham yuvishdi bu. Boshqa odamga yordam berish ham yuvishdi. İkilasi ikki xil ma'noga. Bittasida ular tegishli. Masalan, mehmonlar kelishdi. Ketlar desa ham bo'ladi, kelishdi desa ham bo'ladi. Qizi oyisiga uyni tozalashga qarashdi. Bu yerda birga emas. Yuvdirdi degani bor, yuvg'izdi degani bor. Endi bulardan ikkitadan nima qilishingiz mumkin. Masalan, yuvintirdi, yuvinishdi va hokazo. Ondan ortiq shakl hosil bo'ladi. O'zbek tilini izohi lug'atlariga faqat bittasini berishadi. Hurmat Umarbek degan katta yozuvchi 80-yillarda o'zbek tiliga davlat tili maqomi berish haqida bahs ketganda qarshi chiqqan. Rus tilida 108 mingta so'z bor, o'zbek tilida 55 mingta so'z bor. Rus tilidagi orfografik lug'atda 108 mingta so'z ekan, o'zbek tilidagi orfografik lug'atda 55 mingta ekan. Shuni olganda shunaqa degan. Rus tilida masalan читать, прочитать, отчитать, vычitать deganlar hammasi alohida so'z qilib berilgan. O'zbek tilida yuzib bitta berilgan. Xolos, o'sha funksiyani bajaryapti bo'lmasa, boshida emas, oxirida kelyapti.
Assalomu alaykum, hurmatli bugungi konferensiyamizni ikkinchi kunini davom etamiz. Qo'ldan ishtirokchilar xorijiy mutaxassislar bo'lganligi sababli konferensiya inglizda davom etamiz. Welcome again to the second day of conference. We continue our plenary session. The first speaker is Professor Academician Abdullah Azamov, Institute of Mathematics. The title of the talk on the combinatorial theory of differential equations.
Assalamu alaikum. I also welcome all participants of the conference. I thank organizers of the conference for giving me such an event to tell about my last lectures. Report is devoted to the combinatorial theory of ordinary differential equations. What's the problem? Boys,
Makarna qanaqa o'qib o'tishi? Lozim. Social. Right. Exactly.
in English, science, the whole means only exact. Next. This is the usual problem, or a problem for system coordinate equations. That the y and z are vector functions. The most straight method of approximate solution is Runge-Kutta method. It has many variants, schemes. The general scheme looks like where values of sub g will be calculated equation and according with this formulas. Note please, and in every step we calculate only values of the function f itself. It depends on the integer parameter s. More s, so more complicated, but in order to get such a estimation for the difference between the exact solution and approximate solution, we have to choose some s. For detailed m, from 1 to 4, s coincides with m, but further s and m may be different. Next. Such a scheme will be written with the form of the table called Butcher's table. Butcher's is New Zealand mathematician. This time is maybe more than 90 years old. It is his famous book. It is called Talmud of the approximate methods for the derivation. There is some budget tables for S from 2 till 6. This string for S equal 6, this for equals 5. As you see, derives such a schemes of approximate solution is quite not easy, very difficult. Moreover, it's not really the law. For example, from the scheme of the 6th order, we are not able to derive is equal for S equals 7. So if we need approximate solution of high order, we put the method is not so convenient. In order for mathematician very natural way is basing on Taylor's formula. Formula is well known, but yx is unknown solution. After the formulas, its derivations take part. But these derivations can be expressed by given function f using such a formulas. Given differential system of differential equations, this is usual writing of this next derivative, but further we will use such a brief notation. We consider f and its derivations as operator access to y unknown function.
Sorry, we only see the first page of the slide. Only the first. Is it fine?
That's right. Birinchi betda o'qib so'rayapman.
Yo'q, faqat birinchi betni ko'ryapmiz. Ana endi o'tyapti. Endi o'tdi. 5-betni endi ko'rdik. Bu faqat birinchi bet edi bizda.
Mana ko'ryapsizmi?
Yes. Now we can see it. Thank you.
If there is more aspect, you do derivatives, but the case of vectors, there will be tensors. Instead of multiplication, you should use convolution of tensors. But we may consider as a multiplication. This. So if we observe the formulas for the derivatives, we see such a rule. Instead of f, we put dash f, and here in two ways. Instead of f, we put f double dash f, this way. Instead of simple f, we put this rule. And so we get two summands for the derivation. In the same way, we get some of expression for the first derivation and so on. Further, it will be more convenient to write instead of f the digit 0 first derivative, unit, and so on. So this rule will be written in this form, and this rule will be in this form. Excuse me, I forget to note that here we consider only quadratic systems. For the quadratic systems, the third derivative is 0. It will be more simple. It will be clear than after the system. we talk about this as well, but let us just not concentrate on what is by what system. Let's go. Unfortunately, these two digits shift there. The 0, the 1, 0, and it's such a scheme. Using this, it should be what there's here and while terms of on this term. Oh, I think you understand. So we have special language. Special language. They are given only 3 digits, 0, unit, and 2. And each word will be common in the expression for derivative. And number of the digits equals to the order of derivative. Next. So we get such formula for the arbitrary derivative. This is the list of Taylorian models. For the Taylorian model, is the suit of the models, or this is the set of one. They are different because, as you see in the list of for the derivative, one of the one term maybe took part, may take part several times, and this is according to this formula. What for the quadratic system is theorem 1. We have a criteria where some word written by 3 digits may serve with the Taylorian word for the derivative of the unknown function. The order is clear. The order will be 12 order of derivative. And such a simple criteria. Look at it. Explain it. If we denote by a sub and up k, it is translated into English. The number of words in the suit in the language is sub n up to having exactly k, there is 2. Then such a recurrent formula holds where trans these values, and it's the beginning condition for the recurrent equation. Good. Now we introduce such a notion, a root of a Taylorian model. We erase units and their last 0. Their last letter always will be 0. So we have the root of the Taylorian model. This is taken on the Taylorian models. It means such a unit is the first derivative of the unknown function y of x. It is derivative denoted by unit will be Jacobi matrix. Jacobi matrix. If we multiply after on the left of the this unit always there to the vector quantity. Level 0 is here. Level 2 by linear form. So if we calculate calculations instead on the vectors and by linear forms, we get a roots. There are several roots, and there are number of roots.
These numbers are Catalan numbers.
This number is turns out Catalan number because one of the prophets of Catalan number coincide with the theorem 2. So we may calculate the number of different Taylor models. But this set is this set differs from the list of elements. How define the number of models in the list? This is the second problem. Of the Catalan number, the definition. It's the different ways of calculating product of several elements of the non-associative algebra. All the different definition by agents, the number of ways triangulation of the polygons. This is the monograph devoted to Catalan numbers. Right? United Kingdom mathematician study. Now let us return not only to numbers, but the numbers of the words having changed letters if. For that, we noted that the current formula holds. This is the table of the such number. This is F. This is empty. This is F. This F dot F. F2 dot F dot F dot F. This is no, but the reverse. This is F. This is F dash F. This F dash F dash F. This F twice dash F. And so on. No. Yeah, indeed. This will be F 0, F dot F 1 0 after that. Let's do this. Now, the two, the only one. Control 1, and after that, F5. We continue the debate. So we got it turns out these figures are also well known. Coefficients of the Andrea polynomial. these two pictures from online network ve devam ediyor sequences of the soul. So as you see, these statements are coinciding. There's the interpretation of this sentence is rooted, labeled trees, such as trees, their vertices should be only 1 or 2 or 0. Входящие либо ages 1, 1, 1, 0, 2, 1, 1, 2, 0, 1, 2, and so on. The numbers of such trees are also will be given by the state. Definition of the Andrea polynomials, we consider such a definition equation. We return to the theory from combinatorics, theory definition equations. The beginning parameter is the theorem of Poincaré. So we can build an analytical function on S if we use the expansion of the solution. This coefficient will be dependent on S. This is they are called Andrea polynomials. As you see from this term, the sentence coincide with the with the number from our table. As you see. Next. Corollary. The number of the borders in the list of Taylor are just Taylor numbers because this is corollary, but this fact is well known. The sum of coefficients under polynomials is just Euler number. What is Euler number? Euler numbers is the number of up-down permutations, on the set from 1 to n. For example, if n1 only there is nothing to do. If L2, we have 2 permutations, only lead up down. This is down up. In L3, only 3 permutations up down. Here also 5, excuse me. If L equals 4, from 24 permutations, only 5 will be up down. So this numbers coincide with this quantities. Where formula was shared will be on this. So such a properties were opened by French mathematician André. This Euler numbers coefficient of the expansion of trigonometric function. This can be also taken as a division of the area, not only. So quite a lot of properties of very famous numbers. So we have 2 lists. One list is this of all Taylor forms is a pair expression of the second is the set of Taylor forms. We have very simple criteria when some word on the alphabet 1 to 1 unit 0 belong to the set of Taylor would quite simple criteria. But is it possible to calculate their mark in the list of Taylor? It turns out this is possible. For that, we use reduction of the Taylor number. For reduction, we should go back. Instead of the pair of digits 1 0 equals 0, this is of 2 0 equals 1. So the length of the Taylor number will be 4. Here we have 9 digits, here 8, 7, 6, 5, and after that we can stop because further reduction will be unique. And so such a tree ends with some words. We may call the leaves of this tree. It turns out to the multiple of the word W in the list of Taylor equals the number of leaves in its tree. For example, this word take part in this list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. Good. So we have such an algorithm for as derivative of the quadratic system, the solution of the quadratic system. First step, make the list of roots with car letters where car runs between. For example, second step, make the set fulfilling each root till the word of the length n. So we get this set, the set of Taylor words. And after that, calculate mavzusida of each word from this set. And we get the list and so and up to each set. And after that, calculate the division. But after the next step, we will using Taylor formula for the approximate solution of the Cauchy problem. This Russian mathematicians found such a property, the connection between is also minus between the list of Telegram borders. Such kind of trees from graph theory. These trees are rooted. The second, they label it from digits, from natural nouns. There's two bijection between different Taylorian and topological types of trees. This is one deviation. The second deviation between the list of Taylorian models and the labeled. Well, unfortunately, I couldn't group these two properties. So I comment to study these problems. Somebody is interested. Thank you very much.
Maybe one olan parti.
Yes. But instead of promoted for arbitrary systems, not only quadratic systems, the analogical result. But I have time to do it.
Bu sefer.
Oh, thank you for that.
Speech will be joint talk, Professor Rakan Akut and Dr. Darwin Tabir. The speaker is Dr. Darwin Tabir. Share of the good Junior Patrick. But please.
Thank you very much. My today's topic related to investor programs for space-time technical parallelization on metric star graphs. And my collaborators are Professor Ashur and PhD student Ray. So this is what we consider inverse cost problem. So in the parabolic equation that usually describes subdiffusion, diffusion, and subdiffusion processes, we find unknown right-hand side of the equation. That's called external source. And we consider such problem in metric star graphs. Actually, we can this result will be called for more general compact and connected graphs, but for simplicity we consider just star graph. And star graphs, mostly graphs, is used for investigates different wave dynamics and diffusion processes in the branched structures. And let us start this. So we already have two talks on fractional derivatives and fractional integrals with Professor Ashur and Professor Imanov. So I just shortly review this. The integrals first, we will consider two types of integrals. First one is Riemann even interval or the alpha. This one is called the left hand This is the right integral of the or the alpha. Alpha is 0 and 1. More properties of this integral can be found in the following two ones. These integrals have the following properties. The lambda is further continuous function, and already impressed with the previous talk. This derivative is called capital fractional derivatives. This is combination of usual derivative and fractional integral. And the next one is Riemann derivatives. We can see that these two derivatives just difference just this order of integral and derivative, usual derivative. So, if, for example, if you consider function p over the gamma, then fractional derivative of this function will be in this form. If you put 1 or 2, then you will get the usual derivative of the other function. We should say that, for example, such kind of derivatives is defined in the continuous function spaces. For example, in F is C lambda, and lambda is between 0 and 1, and alpha is less than 1, then the following property is called psi is from the class C lambda minus alpha, and psi at 0 is 0. So as we can see, this derivative has some singularity at t equal to 0. This is left derivative. For our consideration, we need to extend the domain of these derivatives where they define. For this purpose, we introduce fractional problem spaces called problem probability spaces. H alpha is Banach space governmentally by this norm. We put H0 alpha in this way, or alpha greater than 1/2, and define H sub alpha class. And in this H alpha class, we could produce such a norm, and with this norm, it is Banach space. And these results can be found from these two references below. And some results from these two differences. First, we do not see 0, 1 this last, and closure of first lemma. C01 is dense in H alpha. And second, integration. Operator of integration here alpha for 0 is it is for left derivative, left inverted. From L2 to H alpha will be injective and surjective. And there is this constant C such that the following equivalency between not so from the first property, we see that the inverse of E alpha is X. So we can introduce E alpha as the inverse of this integral operator with the domain H sub alpha. So with respect to this derivative, these two norms are equivalent, and we see that. For example, H alpha is very, for example, H alpha is, has some condition from condition. So that says the function at t is 0 should be 0. So, for example, constant is not in this class. So this derivative is not prepared for constant function. So to overcome this, for the case alpha is equal to 1 alpha 1, we can introduce extend this derivative in this way. So we put input of dt minus e0. This derivative is defined and takes this equality as a definition. For right fractional derivative, we can also define generalized some big derivative analogical way. So we skip this part. And next, we should we define a big couple of derivative. Now we should define a big derivative. For this, we use result from exact logic. So this first line is the first time we see well-known identity for Riemann derivative. Using this identity, some generalizing identity, we introduce class AC 0 beta 2. This is defined in this way. This space consists of all functions of the form of this form, where the sum of phi is L2. Comparing these two identities, this is in the classical case, this is for the overall case. We see that instead of this derivative, is comparing, we find that phi is instead of this derivative. So phi is just generalized big derivative in the Riemann USS terms. So second, for the right derivative, we can analytical space, do not AC and some properties characterization of the spaces. So F in AC beta 2 equivalent to the following for fractional derivative or the vector is equal to. And the same for right derivative. We define fractional problem spaces in this form at the intersection of this space of this L2. And the same, we can write in this form. Rho in HP equivalent to the following. Rho is L2 and revenue derivative of rho is L2. It's the same for right inverse space and right derivatives. These two spaces, if we take this following two scalar products will be Hilbert spaces. Okay, now we start formulate our problem. For this, we, for example, consider just star graph, simple case. In this star graph, in each front of this star graph, we define local coordinates by the following mapping, geometric mapping. And for the function u in the graph, we define uk as a restriction of u in the certain form uk, and for us will be more advantageable to use such type of vector type or tensor type notation. Derivative defined in this form, and the product is that kind of tensor product, and we also denote G tau. G tau is a gamma times eurocon. And L2 space in this graph defined by this definition. We can see that this L2 gamma is just direct sum of the space L2 equal. And as this is our problem. So In this graph, we consider the following equation. We rewrite the equation in each form. This equation consists remind you the capital derivative is set to time and such kind of generalization of Laplace operator, fractional order. Laplace operator, it is not this consists capital and remind derivatives and the right and left derivatives. And the right hand side we have ft multiplied by gk plus hk, and initial condition given as I say, equation 2. And at the branching point or inner vertex of the graph, we need to define Kirchhoff conditions. So this is given by equation 3 and 4. Equation 3 is some kind of continuity condition, and equation 4 is current conservation. And the boundary conditions are the boundary points of the graph is given by equation 5. And here we suppose, of course, gamma k is some absolutely continuous function, and gamma k is not zero because it's strictly positive. We divide our problem in two parts. UF, we should find U and F. Divided into first problem, two problems. We start from the second. Second one is called direct problem. So, direct problem formulated as follows. So, we consider the equation where F is 0. And in each case, H and with the initial vertex and the boundary condition defined below. And for inverse problem, we have two unknowns, Z and F. So for this reason, we need one other determination condition given by equation 6. So it's formulated here in this slide. Okay. Some history. Well, history. Similar problems for the case of interval is considered in the first block. They must be very contracted big solution and considered for optimal control problem on the graph on the line is segment. So in the second and third, they considered surely the equations, parabolic fractional Schur equations, considered also optimal control and find big solutions using the same conditions as in our case, but in our case we get more quadratic strong result, and in our case the solution is strong solution for its classical solution. This is energy spaces for the class for our solution. Our solution will be from this class. It's one third. This class I write north of this lot. It is also filtered space of third part. We use method proposed by logic sphere for parabolic equation. We write the problem in the form, operator form. Operator defined by this equation term, and this domain VGT. And the range of this operator in L2G. The problem is if H is L2, then the problem is indissoluble in the energy space.
That means.
Okay. Prove it as the following steps. First, we prove that operator is continuing from DA to LG2 using some estimators. Next. Second, inverse operator is well defined and continuous. And the last step, orthogonal complement of LA in L2 is so then is next we show that there is no orthogonal complement to range of operator in the L2. So the theorem reaching this point, and from these three properties, it follows that the solution of the problem exists under its unity. Unity solvability is proved. Okay, I already mentioned about the problem. Now we got to the so we put this notation and suppose the following conditions are found. Here we write our problem is the operator form. The operator is defined in the following way. D is proper to L2. Now, the theorem is the following. If the conditions K1 are found and H in L2, then the inverse problem has a unique material solution. We prove unity solvability of the inverse problem using to prove this on the use of material estimators. Prove the result of this operator is bounded from L2 to L2. And from this follows that the problem has unity solution. Thank you.
Thank you very much. Any questions? Any question from online participants? If not, thank you again. Now, according to the circuit of participants, we have three. Now, we have 5 minutes for paper. And let us follow the patient class. Five minutes. I thought I was leaving now.
Yeah. Hello.
Hello, we will start after 5 minutes.
Okay.
Start
Good.
with yours.
Yeah,
Okay.
thank you.
Speaker is Liming Liao from Wuhan University, China. The title of Expanding Property and Statistical Law for Public Development. Please.
Okay, thank you. Thank you very much. And it's my honor to give a talk here to report my latest research. Thank you for giving me this opportunity. Okay, so I think you can hear me, right? And
Yes.
you can see the slide. Okay, good. So this is a joint work with Shi Fang, Hongming Nier, and Yue Wang. and I will talk about some periodic dynamics. So I'm not sure if everybody know the periodic numbers. So my talk will be just divided into two parts. One part is an introduction to the periodic numbers shortly, and the periodic dynamics. And the main part is about the dynamics of periodic sub-hyperbolic maps. So I will give you the definition of what is a sub-hyperbolic. Well, anyway, so the periodic numbers, I think most of you know it, but anyway, I will just give you a short recall for these periodic numbers. So usually we give periodic number here, P is a prime number. So we can write some integer, usually, you know it. We can write any integer like in this form. Okay, what is the periodic numbers? So the first one is the periodic integers. You just write in your number. Okay, here is some from 0 to capital N, right? And you just formally let this capital N to infinity, and then it will give you a periodic integer. So in fact, this number is correspondence to a sequence A0, A1, A2. You can look at a periodic integer just a sequence with this AI just from 0, just from 0 to P minus 1, right? Okay, basically you have, in the real sense, you have nonsense for this series because this is, it is a divergent series. So basically we can introduce some new absolute value. This is a new absolute value like this. And then you have the meaning that this is a convergent series. And in fact, in general, we can take the fractional field of the JP of this periodic integer. That means you begin with some special number, not only from 0, and then you can get your periodic numbers. And in fact, if you define like this, then that means if you have Pn and the absolute value is P minus n, and that means this bigger one is not big, right? It's smaller. And then you have convergent. And basically, by this, you define a metric, and this metric is arithmetric. So you have this inequality stronger than usual triangle inequality. So I just want to recall you a fact that this is what we have done here from capital N to ZP, right? I take some N to go to infinity. So this is some closure of this capital N, and you get the periodic integers. Yeah. So, okay, to recall you that our development of numbers, you know, we begin with the natural number, and then by the reason of subtraction, we need to have the integer number, Z. And by the reason of division, we need to go to rational number. And by solving the, you know, and at this moment, you have two way to get your extension of Q. One is by the, you know, the classic absolute value, the completion, you will get the real numbers. Another way, you use this kind of periodic in absolute value, this periodic absolute value, and then you get your periodic numbers. And we want to solve the equations, then you add, you basically, you know, you add some root of -1, and then you get the complex number. But another way, you need to add many things, and then with this many things, you will get the algebraic closure of periodic numbers. But unfortunately, this guy is not complete with respect to the new absolute value, and then you need to do once again the completion of the absolute value, then you get the periodic complex number. So this is a CP. And this time you do not need to add more for the algebraic equation solution reason. because this is fortunately this is also algebraic complete. So this is both complete. Then we get these periodic numbers. Okay, so because this is important, I will work on the dynamics on the periodic numbers. So you should know a little bit these periodic numbers, right? And in fact, my talk will also go to the finite extension of these guys. For example, if you add some kind of minus or some root of p, something like this. This is an example. You have some extension. So I will work on this. And I also will use some the Noen study on the dynamics on the periodic complex numbers. So we will see a little bit later. So this is a number, the object. So I told you that you can look at the periodic numbers like a sequence. But another way to look at the periodic numbers is by the tree. So you can look at this like a tree. So with the P branch, right? Like this. And the bigger one, and you go upper, like this. So this is another way to look at your periodic numbers. So one periodic numbers usually like this is a array go to infinity. The boundary of this tree is the periodic numbers, right? Okay, with this object, we can do some arithmetic. That is the addition and multiplication. So, for example, if you get this sequence p minus 1, p minus 1, p minus 1, so this is a periodic numbers, which is also a sequence. But if you add 1, you need to consider the carry. So if you add 1 here, you get p here. P is 0, but you need to get the carry here. So you get 0 here, and you get 1 here, a carry 1 here, and 1 with this one, you get also 0, but with some carry here, right? And then you go on like this, you will get this guy at 1, it's just 0 because everywhere is 0. So by this, you also know minus 1 is just this number. So x in this sequence, p minus 1, p minus 1, p minus 1, is just a minus 1. Okay. Okay, you can do the same thing like the multiplication. So you, for example, if you multiply by 2, you get 2p, basically you get 2p minus 2, right? But you with 1p carry here, right? With 1p carry to the second place, and you get p minus 1 for this position. And you do the same thing, you get 2p minus 2, but with the carry 1 here, you get p minus 1, something like this. And then you will get 2x is this. This is nothing, it's not minus 2, right? It's reasonable because x is minus 1. Okay, anyway, so by this, you can define your polynomial and rational map. Yeah, rational map, just some polynomial here and some polynomial here, right? This is rational map. But polynomial is just, the addition, multiplication, or subtraction. And with the division, then you can get the rational map. This is rational map, right? Okay, so you have this, and you have your space, you have your polynomial or rational map. This is serve as some transformation or functions. Then you can get the dynamics. But before I go to that line, I want to recall you, I also want to consider the projective line over QP, because here some point some point gets 0, and with divided by 0, then you will go to infinity, right? Then if, for example, if your rational map is this here, and then by this you will get f0 is infinity. So this infinity is also some normal number. You should not put this infinity aside. So I want to include the infinity. That is the reason why I needed the projective line. So the projective line is also classically you can define if you have some multiple and you look at these two couple, the same. But there's some formula you can you can define this projective line, and you can define some metric here by this formula. but this is just like in the real case, how you get your real line goes to get a ring, right? You just add infinity, you put your, this is a line, your infinity is plus infinity and minus infinity here. But if you join these two together, you get join this together, you get a ring, right? This is your project line of real numbers. Number is the same. You recall that you have this tree, this p equal 2, for example, p equal 2 here. You have a tree here. This is your JP, right? And you divide, then you get two branch. But you upper, if I draw the picture like this, you will know this is JP, right? This is J2. But your upper floor, you still have the same thing, right? This is this point is 1/2 J2, something like this. Okay, then you get the infinity like here, like this, right? But this is the infinity. And then the project line, just you want this infinity point to be a normal number. It's the same thing like it's the same thing like a 0, for example, right? If you look at this 0, for example, if you want to look at this number and this 0, it's the same thing. How do you do it? You just low your list line like this. This is exactly your infinity point. This is your infinity point like this. But you want to take this list number and list 0 is the same thing. It's the same thing. So with the same tree, you take these things, and then what is the project line? This project line is just a Keller tree, right? This is a Keller tree. Okay, this is the p equal 2. This is the p equal 3, like this. This is also a Keller tree. So project line of periodic number is a Keller tree. It's nothing. It's just like this. Okay, then now I just go to the periodic dynamics. So periodic dynamics, usually we just take a space, which is a periodic space, a transformation. So you have dynamics. So the beginning of periodic dynamics, maybe we can cite this. Maybe this is the earliest one, and then the famous one, maybe the Hermann Yorkes, who studied the complex periodic dynamics. And we should mention the important work of Woolwich, which introduced periodic number to the physics, the famous string theory. Well, anyway, for me, I'm interested in the polynomial and the rational map. I have told you that these two transformation, and I consider this to be dynamics on this kind of simple periodic space, JPQP or projective line, or this is a finite extension of QP, or the project line of this finite extension. Well, anyway, usually we study the periodic dynamics. We have two classes of different dynamics. One is you can see some isomorphic one or isometrical one or attracting one. This is what we call one Lipschitz, because this is, you have a constant, Lipschitz constant 1 here. I call it one Lipschitz. The other one is expanding. The distance of x, y is larger, becomes larger, so expanding. So for these two different dynamics, usually we can, for example, we can look at two famous examples. One is x plus 1. X plus 1, and then if you iterate, and what's this? This is x plus n, right? And then if you take the closure, so if you take the orbit, the closure of the orbit, what is? This is just the x plus n, the closure, right? But if you remember, I recorded you that this is dp, right? With some translation, there's nothing. And this one is exactly dp. So that means for adding x, so every orbit, that means for all x, your orbit is dense. So this is, we call it minimum in dynamics. So every orbit is dense. So that means you have JP here. But if you take any point here, but the orbit will be dense here. This is the minimum. Any point, any orbit. Okay. So this is the one Lipschitz dynamics. Because if you want to calculate fx minus fy, well, the constant cancelled, and this is what? This is exactly, well, it's nothing. It's Lipschitz, one Lipschitz, and furthermore, it's isometric, right? But another one, if you look at this, you will have fx minus fy. Well, it's some kind of p. Well, so you enlarge your distance. This is an expanding dynamics. And this expanding dynamics, we can prove that this dynamics is conjugated to some shift on the symbolic space. So you have symbolic space, that this space, this is a sequence. It's a sequence. Well, with each xi is just in 0 to p minus 1, right? This is a sequence. What is the shift? Shift just you delete this the first digit. Yeah. So from here, yeah, you just from x0, x1, now you get x1, x2. So this is quite simple dynamic, symbolic dynamics. It's the same as this periodic dynamics. So usually you have two different model. One is one Lipschitz, another is expanding. So let me just cite many works on the study of one Lipschitz. Well, you can find many names. Maybe you know Kennikov, for example. I think you know him. Anashin, very important work by Anashin. And maybe I have never met him, but maybe you might have met him, met this guy. I don't know. And yeah, also some Chinese guy has some study like this. Okay. And for another things I want to mention, that is I work with Aihua Fang. We found some minimal decomposition. That is, I'm not only look at the minimality of the whole space, but in general, if you have a polynomial with degree larger than 2, then your space will be have 3 parts. One is periodic orbit, some minimal parts. That minimal parts that you take any point and it will go like this. It will go like this. And another part is some attracting parts. So basically, the polynomial, you have some global picture for this dynamics. I also want to mention some work on this direction, and you can find some our group, Chinese group, and also some Korean group working on this minimum decomposition. Okay, for the expanding case, you can also find many people, and especially you can find Mukhamedov and Kakimov. I think he was a student of Rozikov, and yeah. Okay. Nice to meet you. Okay, Sablov, and also my joint student with Sablov, Ahmad from Malaysia. Okay. For this expanding case, usually we have this sort of. In fact, this is my first paper in my career. So I proved that in some expanding case, usually you can describe your expanding dynamics with some shifts. And this shift maybe it's not the shift I told you, a little bit complicated, which is determined by some metrics. And this is in fact a finite state of topological Markov chain. Yeah. So by this work, maybe you can do some application. That's because some people, maybe some of you are interested in the periodic Gibbs measure on the Keller tree. And basically, if you want to prove the existence of the periodic Gibbs measure, and then you need to prove that some dynamics has many periodic orbits. And then by this, we conclude by this, then you will have many periodic orbits. And then you can say there are many periodic Gibbs measure. Yeah. So this is the principle to do this. And then also you can find many works. Yeah, I have already mentioned your name. And also in my paper joined with Ahmed and Sablov. So, and yeah, I should not miss, there are many works on the rational maps on QP or CP, especially Mukhomedov and Lozikov. This is a group. You have done lots of work. If also Satalov, I don't know if he's also here. No? Yeah? Okay. Nice to meet you. Yeah, good. So there are many people study, and also you can find some very recent work, so I should say there are many works on this direction. And okay, let me, I have a few minutes, but I need to go to my main works. So this is a sub-hyperbolic map. What is this? What's this? But before I tell you the story, I need to mention two important notations. It's Fatou sets and Julia sets. You have Fatou sets. It's just the classical definition for the complex dynamics. If your family is equicontinuous on the neighborhood, and then you have Fatou sets. And now the complement is called the Julia set. But basically, you can imagine the dynamics. This is usually on the Fatou set is one ellipsis, but on the Julia set expanding. So it's exactly what I told you, these two different dynamics, or these two different sets. And the expanding things usually will be described by Markov shifts. Yeah. So now let's just consider some finite extension. Yeah. If you don't want to go to the finite extension, you're just thinking about the QP, right? And also the projective line. Now I consider some rational map. Okay, then I will give you a general description for this sub-hyperbolic. What is sub-hyperbolic? It's a critical point. If you every critical point, critical point just the derivative equals 0. And the orbit of the critical point will be finite. That means finite. And then this is some x0, which has the derivative 0, and then the orbit something like this. Yeah, some eventually periodic is finite. Yeah, then and go back, go like this. If you go like this, this is finite. And for this, then we can prove that you have only So this you need to go to the countable state, not only finite states. Some countable states you can describe this kind of sub-hyperbolic dynamics. But on the Julia set, but not exactly on the Julia set, you should delete some we call the grand orbit. Yeah, some trivial things. Delete some trivial things, then it's exactly some countable state Markov shift. Yeah, we have the description for this kind of dynamics. And then what is the expanding property? The expanding property, basically expanding, but this is some general definition of expanding. It's not just, you can imagine this is expanding. It's quite easy, but maybe this definition is a little complicated for you. But anyway, first we will see some admissible function. This function is a positive function. So in some neighborhood, you have some positive function, but you have some blow up on some finite many points, but not too much. You have this property. That means you blow up, but not too much. Yeah. And what's expanding? Expanding is with respect to some metric. So some very special metric defined by this. This is Haar measure. With this Haar measure. Haar measure is something like a Lebesgue measure. and with some positive function, right? Then you can define some new metric. With this metric, you have, okay, if you look at phi is the identity function, then this means the derivative is larger than 1, right? It's larger than lambda, larger than 1. So this is in general some expanding property. Well, this definition also comes from the complex dynamics. They have done some similar things by this kind of expanding property. Well, anyway, but our theorem shows that subhyperbolic, if and only if you have this expanding property. Yeah. But the condition is that, the condition is not so strong. It's degree larger than 2. And this is not exactly some important condition, because we can also change the coordinates to let your infinite point is in your phi2 set. This is phi2 set. Okay, more application is something we can do some topological pressure and equilibrium states. So this is some, in dynamics, classically we define like this. You have some entropy, some integral, you take some supreme, then you define some pressure. And the measure which realize this supreme, we call the equilibrium state. And another two, just the back of some, this is this is some, given some potential function, you have back of sum. This maybe you know this definition, easy definition. But this is a sigma, some kind of variation things, if you want to calculate the variation of f. But this is defined, this is if you divide by n, this is the mean, right? So you have mean and the variation. So you can guess what I want to do. I want to do this central limit theorem. This is divided by n. This is the mean minus mean divided by the variation. You will get some central limits theorem. So this is comes from the expanding property, and I will assume some density property. But maybe I will show you why I need this. But this is not a strong condition. Well, anyway, by this expanding property, you can prove central limit theorem. You can prove some law of iterated logarithm. You can also take some mixing property, the exponential decay of correlation, and you can get also the larger deviation principle. Yeah. So I think my time is out, but I just want to say a little bit of this condition. This condition is not so strong because this also comes from some a famous conjecture is saying that the repelling periodic orbits are dense in the Julia set. If you have this, then my condition is nothing. It's quite weak. So I mean, this is the Julia set on the closure of periodic numbers is dense in the Julia set with respect to the CP. So this conjecture is still open, but anyway, there's already some positive results. So I think I should stop here. Thank you very much.
Thank you very much. Thank you, Professor. Any questions to the speaker?
Yeah, maybe I was too fast for the latter part. Sorry.
Hi, good.
Maybe I go back to the central limit theorem.
The theorem is for discrete time dynamics.
Sorry?
Discrete time dynamics for this. So always we consider discrete time of your dynamical systems.
My dynamics is still this. I always take this sub-hyperbolic rational map. So this is my dynamics. Sorry, I changed the notation. So This is a rational map. So with respect to this dynamics, so this guy is this guy. I should change the J. So with this iteration, this is the dynamics. Yeah.
This is a classical definitions of the real
So,
case.
yeah. So this means just GJ plus G with this dynamics. Plus G phi J. So this is the dynamics, and phi 2J go to G phi n minus 1J. So this is the back of sum. Yeah.
More question?
Yeah.
And in this case, thank you again.
Thank you so much. And welcome to China, maybe. Bye-bye.
So the next speaker is Amina Al-Ahmed from United Arab Emirates University.
Amina, are you here? Do you hear me? You did not speak out. I couldn't see her. Hello. In this case, change.
Maybe we will.
Yeah. Maybe next speaker is the top. Mahmud? Do you have it?
Victoria bilan sko'shaydi.
Chiroq o'chgandir Saudiya Arabiyada.
Victor, how are you? Are you ready to give a talk now? Where?
You are talking about me, Utki?
Yeah, because the next picture.
Can you listen me?
Okay, next picture will be. You will talk about.
Can you listen? You are talking about me?
No.
Can you listen me?
Yeah. Now I'm listening, but your talk will be at the time.
Yes.
Mansur, would you have?
I cannot listen you properly. Can you listen me?
Alo, assalomu alaykum.
Can you listen?
Assalomu alaykum.
Tamam.
Assalomu alaykum. Eshityapsizlarmi?
Yeah.
Okay. If you are
Diqqat
ready,
diqqat berishim mumkin. Bemalol vaqtim bor.
Okay, thank you. We will continue our planning session. So, since our map is not here, we will give the next speaker. The next speaker is Mansur Saburu from the American University of the Middle East. Why? The title of Stable and Historic Behavior in Replication Equation. Mansur, please.
Okay, xo'p, rahmat. Assalomu alaykum, hurmatli ustozlar, konferensiya ishtirokchilari. Katta rahmat. Avvalambor, kecha imkoniyat bo'lmadi. Bugun o'sha imkoniyatdan foydalanib o'tkir tug'ilgan kuningiz bilan tabriklayman. Sizga sihat salomatlik, oilangizga xotirjamlik, ishlaringizga rivoj tilayman. If you allow me, I want to talk in English. Can you hear me? The slide is visible. Can I move on? Please, if any issue, please, Abrar, can you remind me if there is any technical issue, please? My voice is clear, right? Can I continue? All right.
Yes,
so,
you can.
Okay, good. So I want to talk about the stable and the historic behavior in replicate equations. And basically, I want to discuss some two different class of replicate equations in evolution game theory, which were generated order preserving operators. And this one of the class has fork theorem of evolution game theory. I will discuss in a while. What does it mean? The other one has a kind of completely different behavior, like opposing behavior. That's called mini-historic behavior. So what does it mean is that the time average of the orbit will slowly oscillate during the evolution of the system and do not converge to any limit. So the purpose of this talk is to present in some class of evolution game theory can coexist two different kind of opposing dynamics. So that's what we want to share it here. And this is today's talk is kind of general framework which was developed during the last couple of years. So I don't want to discuss details of the proof, but the interested reader may refer to these papers. And during the last few years, it was developed in this series of the papers. So now I want to just recall two main theorems in ergodic theory. In ergodic theory, suppose that we have a measurable space, and the evolution of the system is generated by a measure preserving transformation. And you can look at the orbit of this initial point. And now, for example, suppose that you want to observe some physical phenomena, for example, speed of the particles. So you have here observable, which maps from the space to the real numbers, so that you can generate this number sequence, like f of x, you calculate the speed at the initial point, then you calculate iterations, all these speeds of the particle. Well, if the system is ergodic, evolution is ergodic, then Birkhoff individual ergodic theorem states that this time average converge and equal to the space average. In other words, the average speed of the all particles at some given point is equal to the average speed of the one individual particle over the time. So that's why this is called as individual ergodic theorem. And we can look at for this the same ergodic theorem from different perspective. We can introduce Koopman operator, so which associate for each of the observable, new observable, defined by T, this induced mapping. And the good thing is that the space of the all observables are vectors, is a vector space. So you can add them, you can multiply them, you can iterate them. And this allows us to study, instead of studying the number sequence, the average of this number sequence, you can study the average of the vector sequence. And by that time, in late 20s and early 30s, von Neumann, he already developed a spectral theory of the bounded operators acting on Hilbert space, and he masterly utilized all these techniques, and he proved for Neumann in 1932 that this average, the mean operator, this mean average of the operator converges to the space of the fixed point of the operator, and this as orthogonal projection to it converts to orthogonal projection that maps to the space of the fixed point. So these two different theorem plays very crucial role in the ergodic theory. Now we can introduce now level sets. So for given alpha, we can define all initial point where the time average converges to that alpha. And we can also introduce irregular set where this time average does not converge. So now we can decompose all the space X like multifractal decomposition, where the converging set of the converging the set of the initial point where the time average converge, and then we have here irregular set. This irregular set is negligible in the ergodic theory, which says that the measure of this irregular set is zero with respect to any invariant measure. So we can discard this set. However, in multifractal analysis, this irregular set where the time average does not converge could be as large as whole space. And sometimes it's a large set with respect to some physical measure, like Lebesgue measure. That's why, motivated by this issue, David Ruel, in early 2000, he introduced a concept of historic behavior. We say that this orbit has historic behavior if there exists continuous function, f observable, such that this time average does not exist. In that case, we call this system has historic behavior. In a simple language, it means that the orbit starts having new ideas about what it wants to do, keeps on changing considerably, so that the value of the time average gives information about where it was, the particular where it was location of the trajectory. So that's why it's witnessing the history of the dynamical system, and that's why Ruel, he coined the name of the historic behavior. So, like, if you want to put an analogy, like ergodic theory case, we can introduce two types of the historic behavior. One of them is individual historic behavior. We say that if this time average, this time average does not converge for some continuous function f. Or we can discuss mean historic behavior, where you can keep the operator and then you start in the vector space, you start to average take the average of the orbit, and this average does not converge. So we can distinguish these two types of the historic behavior. All right, so during the right after this definition, Tucken, he proposed a problem that can we describe persistent family of the dynamical system that has historic behavior? Because an issue is that sometimes if you may propose some model, but this model may not accurately or precisely describe physical phenomena. And maybe you can have some fluctuations due to the massive data information or some human error. So that's why if your quality of the dynamical system is persistent under some perturbation or some fluctuation, and this quality preserved, then this kind of model can precisely describe the actual physical phenomena. So for that purpose, Tucken proposed a problem. Is it possible to describe this as a historic behavior? Is it kind of persistent, or under some perturbation, this behavior can be disappear? So he proposed a problem to describe, if possible, this kind of dynamical systems. And during the recent years, under the name of the Tucken's last problem, this problem was solved, and it was published in very prestigious journals like Advanced Mathematics Proceedings of the AMS or Journal of American Mathematical Society, and many journals. So this problem take attention of the researchers, especially Japanese school and the Tucken's school in Brazil they studied this Takens loss problem, and it was a very important problem in dynamical system as much as stable cases. Right in early 2010s, right after this IHS, Professor Azikov also introduced in Tashkent School of Dynamical Systems, he brought to our attention the Ruel's concept of the historic behavior and the Takens problem. And so Professor Azikov, he recognized the importance of the problem, and he tried to bring the people under one umbrella and create a platform and try to connect our research with these Takens problems. And especially I had some occasion to discuss about this history of these problems. I'm very grateful. And you can see there is some references till now, before it was used to call non-ergodicity, and it was done by many authors, including Professor Ganhajev Nasir Nabievich, Professor Ganhajev Rasul Nabievich, Professor Mohammedov, and his students. So they did all this. They tried to solve Takens problem in the mean historic behavior cases. So now Japanese school and the Takens disciples, they were working in the individual historic behavior, but here in Tashkent school, they concentrate on mean historic behavior. Here is a bunch of the references. So now I want to give some examples for this kind of dynamical systems, brief examples. Now, according to the Takens and the Ruel, the first example was given by Robert Bowen. And you can look at this flow on the plane, planar flow. So you have here two saddle points, P and the Q. And so that stable manifold of the P is connected with unstable manifold of the Q, and vice versa. Stable manifold of the Q is connected with the unstable manifold of the P, and with some eigenvalues, lambda and mu. And so that this boundary generates kind of heteroclinic cycle. And you may have inside some source, a kind of repelling fixed point. So whenever you start inside, it will repulse, it will push you to the boundary, to this region. And if you assume that the product of the ingoing speed is larger than product of the ongoing speeds, then the cycle, heteroclinic cycle, becomes attractive. And Takens, he showed that in that cases, in this example, we can show that this time average does not converge. And this was done by Robert Bowen, and he didn't publish it, but eventually Taken, he gave a precise mathematical proof using the geometric structure, and he published in this paper. And there are many other examples also, like this kind of zero-sum games, or this Lotka-Walter equations. And we can also have here simplex, two-dimensional simplex, and you may have a corner of the simplex, saddle points, and the boundary is, again, a boundary of the simplex is a heteroclinic cycle. And if you assume that the ingoing speed, product of the ingoing speed is larger than product of the outgoing speed, then this boundary also becomes attracting. And for this dynamical system, we can show that this time average does not converge. It has historic behavior. And there are also other examples. I will skip this part. Maybe one is interesting example in this talk is this Stein-Ulam spiral operator. Ulam and Stein, they introduced this kind of discrete dynamical system. It's known for us as quadratic stochastic operator, or Walter operator. So this simplex has three saddle fixed points, and the center is repelling, like an analogy of the Bowen's eye example. So here, unlike to the continuous case, in discrete case, you may have a cycle, boundary cycle. However, it's not heteroclinic, which means that it does not fill up the boundary of the whole simplex. So omega limiting set will be it will be inside of the boundary, but it may not coincide. So Ulam conjectured that probably this time average converge. Later on, Zakharevich, he showed that no, this Q has historic behavior, meaning that this time average does not converge. And in 2010, Muzirevich and Baransky, they showed that there is inside a point you can find, so that this omega limiting set will cover all the boundary. And this kind of initial point is not small. It's a residual set. It's large. And the Hausdorff dimension of this set is more than 1. So, and when I talked with Muzurewicz, and he told that this problem was brought to his attention, Lubitsch in the conference, so that he got interested in this problem. And so based on this example, Stuck can make we can say that, make a prediction for persistent historic behavior. He said that certain dynamical system found in evolution game theory and the population dynamics could exhibit persistent historic behavior through the presence of the attractive heteroclinic cycles. In contrast, it's a common belief that the most of the reasonable replicate equations satisfy the Folk theorem of evolution game theory. So meaning that the Nash equilibrium is a rest point, fixed point, stable fixed point is Nash equilibrium, and the strictly Nash equilibrium is asymptotically stable, and any interior orbit converge to the Nash equilibrium. So this is kind of common belief. Most of the reasonable dynamical system obeys, adhere or fulfills this kind of theory. Now, my talk is to challenge this belief. I want to show that, I want to demonstrate that there is 2 classes of the dynamical systems in the replicate equations. We can observe stable as well as historic behavior. They can coexist together in one system. And this is something is interesting. And the class of these mappings are persistent, and it is very vast, very large. So we cannot ignore one of the classes. And I want to also confirm that Tucker's prediction also true by providing some vast class of the dynamical systems. In this talk, I want to discuss mean historic behavior mainly. I will concentrate on the mean historic behavior. I want a little bit digging deep inside of this historic behavior. I want to comprehend and understand what's going on in these cases. Let's try to discuss a little bit about this cases, historic behavior. We have an initial point. We generate orbit of the given transformation or continuous operator acting on any dimensional Banach space. And then the question is that, does this orbit converge? If it converges, then we call this system stable. And the question is that we will describe all stable states. If not, if the orbit does not converge, then probably we'll look at the first average, try to make it the system smooth, and the regular will start to take an average of the given sequence. And the question is that, does this first average converge? If yes, if it converges, then we call the system is ergodic. And now next question, we've described the limiting set of this time average. If not, if the time average does not converge, then we call the system is a historic behavior. It has a historic behavior. Then we can continue this process. Since the first average does not converge, probably second average does converge. So that's why we take the second average, and we continue this process. If the second average does not converge, then we'll continue. Now question, when it will last, how long it will last? Is it possible after some time, after 5, 10 average, this averaging process will stop, then it will be converging system? And this was proposed by Bonatti, Deis, Marcelo Viana in his book. And they say that the high order averages might provide some classification of the dynamical system to indicate some statistical complexity. So for that purpose, they encourage us to study the high order averages. Now, if you have here any dimensional Banach space, I introduce here the orbit of not only one operator, non-autonomous systems, and you can construct average in a proper way, and you can introduce high order averages. Now, some of the kind of dichotomy universal phenomena for any dynamical system says that either one of these statement holds true, either one of them. Either this k order averages converge for any k, meaning that first order average, second order, any order average converges, or any high order averages diverges. Like if first order diverges, then second order also diverges, third order diverges, and etc. So either one of these phenomena can happen. This kind of universal phenomena for the compact dynamical system acting on the Banach space, infinite dimensional Banach space. And it was announced briefly in function analysis, then it was generalized finite dimensional case and infinite dimensional case. Now, as a corollary, we can see that we can have a picture like, so stable case, the orbit always converge. That's fine. Now, ergodic case, the orbit may not converge, orbit may diverge, but the time average converges. In the historic behavior case, orbit diverges, the first order time average diverges, second order, etc. So the averaging process it will not stop, never. It will continue. So you see that the stable behavior and the historic behavior, opposing dynamics, it's very distinct dynamical systems. So the question is that why this happens? Is there any mechanism to cause this historic behavior, that wild dynamics? Is it possible to understand? So that was our next step. And then in this theorem, we use generalization of the Hardy theorem, which was proved almost century ago. And Hardy, he proved that if you have Cesar means summable sequence, and if its number sequence is big O 1 over n, behaves like that, then the sequence also is summable. And we prove this theorem in Hilbert space, in Banach space case, in n-dimensional Banach space, if you have a vector sequence, and the norm is behaves as big O 1 over n, then it's also summable. And we were wondering whether we are the first one who proved this theorem, or we overlooked in some literatures did it prove it, because Hardy, he proved almost century years ago. So then we asked from experts, they say that no, even the transition from real sequence to the complex number sequence is kind of complicated because of the order structure, and due to our short and elegant proof, we managed to go from real numbers to any Banach space, and they say that it's a new result. Now I want to give some preliminary introduction here, the concept from evolution game theory. Since I have limited time, I want to skip all these parts. So now I want to give replicate equation. Replicate equation describes the evolution of the replicator, which if the fitness of the species is larger than average fitness, then the species will survive. It's a kind of law of the nature, right? If your performance, your fitness is larger than average people, then you survive. If your performance or fitness is smaller than average fitness or performance, then you may not survive in this environment. So this is a kind of replicate equations, and we can write in a discrete dynamical system case in that form. And now we can introduce similar order preserving. So we call this operator similar order preserving. If xi is larger than xj, then the outcome was larger component wise. If smaller, then outcome also smaller. Then if they are equal, then they're equal. Meaning that in biological meaning that if you have species, dominating species has dominating fitness in that sense. So we can introduce a lot of examples for this kind of mapping using Schur convex function, using convex functions. And here is a concrete examples for the similar order preserving generated by Schur potential functions. Or sometimes you can also use the gamma function to generate similar order preserving. So here is a kind of class of the similar order preserving is large. Indeed, by using the previous examples, you can generate larger class by choosing addition or compositions or multiplication. So the class is very huge class. Now, during the couple of years, we managed to prove this folk theorem of evolution game theory for the class of similar order preservings. Initially, we we consider some examples. Eventually, we consider Schur function. Then eventually, we generalize to the similar order preserving case. Now, I want to discuss a little bit time about the historic behavior, how we can observe. According to Ruel, and he gave a kind of, he outlaid a kind of how we can observe historic behavior. According to him, I can read it, his quotation here. If you can assume that this evolution of the system is as a random wall in a random potential, random environment, at some given point, the evolution will trap it in some valley, some places, and then eventually it will get out from that place, and then after some time it will come back and stay there longer. And by this way, we can create historic behavior. He was just giving a kind of beautiful idea how we can observe historic behavior. Recently, we tried to put it mathematically to give mathematical formulation of his idea, and we introduced a kind of cheap version of Ruel's and Tuckin's idea. We call this uniform historic behavior. And now I can introduce this concept. You can have a 0-1 sequence given this way. I say that the 0-1 sequence has a gap. Sometimes it's called Hadamard gap. If the distribution of the 1 and the 0 has this kind of distribution. And you can imagine now you have some set, you start to screen up orbit to trapping and escaping time in this region. So we generate here 0-1. If it's inside, we call this 1. If it's outside, we call this 0. And now if you have two convex disjoint sets, we say that orbit has uniformly historic behavior, U1, U2 historic behavior. If there exist numbers depending on X, so that this trapping escaping sequence has a gap. And we can collect these initial points, and we say that continuous dynamic system, compact continuous dynamic system has uniform historic behavior if there exist two disjoint convex compact sets such that this historic initial set has physically large, meaning that it should have positive Lebesgue measure. And we can prove that for any initial historic behavior point, this time average does not converge, and it has historic behavior. In other words, the uniform historic behavior implies mean and individual historic behavior. Now, here is some beautiful, this beautiful interpretation in mathematical biology. I will skip up this part, probably I don't have much time. Now, I want to discuss a little bit Tuckin's problem. I want to give you a concrete example, which exhibits historic behavior in a persistent manner. So we have given here either one of this equation 1 and 2, and you can define here, this is a rock, paper, scissors game, and you can define here density payoff matrix, depends on density distribution. And for this equation, replicate equation 1 or 2, we have historic behavior. Moreover, this time average, high order time average, does not converge, meaning that this uniformly historic behavior, it's enough to cause wild dynamics, like you start to average up the process, but it may not converge at all. So that's a mechanism why we can expect this kind of wild dynamic systems. And this was initially started, and then we consider some examples. Eventually, we generalized to this general class of similar order preserving mappings. Now I want to show that why this dynamics exhibits in the persistent manner. Here is this equation is defined by 3 parameters, a P point, function F, and a G function. And we introduce suitable topology here. And we say that this replicate equation exhibits historic behavior in a persistent manner if there exists open neighborhood of each point, of this point, such that for any point inside of this neighborhood, associated replicate equation exhibits historic behavior. Like small perturbation will not cause damage in the historic behavior. So then we show that if you pick up any interior point P, and if you pick up any increasing function, any, and if you pick up any non-vanishing continuous function, then this equations 1 exhibits historic behavior in a persistent manner, meaning that small perturbation or fluctuation in the mappings will not cause any damage to the historic behavior. So we can give some concrete examples. We can have from mathematical biology, we can pick up some functions, concrete functions, and we can see that here this mapping 3 has uniform historic behavior. So it's formulated in terms of the parameters. You can change a little bit parameters, still it will exhibit historic behavior. And there's some other examples here. And that's it. Thanks for your attention.
Thank you. Second point. Any question? If any question.
I think you have an example where
Yes.
the set of limit points coincides with the boundary of simplex.
Yes, please.
Can you
Yes.
go through this example? It's
Yes, please.
interesting.
Okay, just 1 minute, please.
Assalomu alaykum. Bu bitta savol borda.
Yes, assalomu alaykum, Ostonbek. Eshitaman.
Salom, Masur, yaxshimisiz? Your definition of stable a little bit strange. The stable means something a little bit differs. Stable ustойчивость yoki bir sal qimalaganda o'zgarmasligini bildirardi. San tarafingda faqat yaqinlashsa bo'ldi deyapti. Shu yo'q qanaqadir boshqa ma'noda stable deyilyapti. Shuni tushunmadim.
Aha. Haligi o'tgan aka agar ruxsat bersangiz qaytib kelaman nimaga savolingizga ruxsat bersangiz agar. Faqat in this I just to pick it yes there is various definition of the stability like Lyapunov stability or like asymptotic stability, but I just here briefly say that convergence just to make it this discussion easy. But when I discuss in this theorem when I discuss Folk theorem stability here, sorry for this one, where it was. When I discuss the stability Folk theorem of the evolution game theory, I mean this Lyapunov stability. Like some neighborhoods will stay there after some iterations, and from that neighborhoods, if you start to any point, it converges to the fixed point. So in these theorems, Folk theorem of the evolution game theory, I assume that asymptotic stability and the Lyapunov stability, both conditions, I assume it. But only just discussions, I just mentioned briefly convergence. Here, I said it's here, right? Yes. I'm sorry, just 1 minute, please. In these theorems, I assume that Lyapunov stability and the asymptotic stability, this stable means in that sense. And if I come back to the question, 1 minute, please.
One more question.
Yes, please. Yes.
Demak, xorisanda agar average yaqinlashmasa, hamma qolgan averagelar ham yaqinlashmaydi.
To'g'ri.
Shunaqa rezultat chiqyapti, to'g'rimi?
Shunaqa.
Boshqa neydi? Boshqa akslantirishlarmi, boshqa fazodami, boshqacha tipli akslantirishlar. O'sha ham shunga o'xshagan narsalarni qilsa bo'ladimi yo bu qiziq kutilmagan natijada. Yaqinlashmasa, men o'yladim bir qanday klassifikatsiya qilib bo'ladi. Bir qadamdan keyin yaqinlashadi, unda qiziq har xil narsalar chiqardi deb o'ylardim.
To'g'ri.
Lekin natijadan keyin qizoqroq tuyulyapti.
To'g'ri. Agar mana shu natija bo'yicha agar mana bu ketma-ketligimiz demak uzluksiz funksiyani orbitasi bo'ladigan bo'lsa, uzluksiz funksiya bo'ladigan bo'lsa, u holda agar birinchisi time average yaqinlashmasa, boshqalar ham yaqinlashmaydi. No, agar measurable mapping bo'ladigan bo'lsa, ya'ni discontinuity bo'ladigan bo'lsa, unda aytayotgan natijalar kutilishi mumkin. No, agar uzluksiz bo'lsa, ya'ni demak the mapping is continuous and mapping on the convex compact set in that case is if first average does not converge, then the rest will not converge. But if you have measure preserving like discontinuity, some other property, maybe it will create what you expect, like maybe after some time it may converge. So this is the theorem is true for any continuous mapping. But if it's measurable, we can expect different phenomena.
To'g'ri, qanaqadir Markov zanjirlar, boshqa narsalarda, qanaqalarda bo'lishi mumkin, ha?
To'g'ri, bo'lishi mumkin, kutilishi mumkin, shunaqa ketma-ketlik qilishi mumkinki, qanaqa darajasi yaqinlashmay qoladida, lekin undan keyingilari yaqinlashib qolishi mumkin.
O'sha qiziq bo'lardi. O'shanda
mumkin. No, agar bu yerda uzluksiz bo'ladigan bo'lsa, unda haligi shunaqa nima situatsiya yo'q, kutilmaydi. O'sha demak.
Удивительный результат, hech nima deydi, tushunish qiyin, qabul qilish qiyin deydi.
To'g'ri. Buni asosan mana bu Hardi teorimasidan kelib chiqdi asosiy narsa. Endi biz hayron bo'lgandik, bu natija isbot qilganmi kitoblarda biz.
Yo'q, oldin ham eshitganman, menga ham gapirib bergansan, baribir hali ham o'sha natija qilyaptim.
To'g'ri, xo'p, tushunarli. Agar ruxsat bersangiz, o'tgan ekan savoliga qaytib kelsam. Yes, here is example. This Ulum's classic example, what we study here. This quadratic stochastic Walter operator. And in this case, and Mizurevich and Baransky, his student, they proved that you may have a large set of initial points, not like negligible, large set, residual set, where this orbit of this initial point covers all the boundary of the simplex. And the discrete case, it's very hard to believe because in continuous case, you can expect the coverage of the boundary because it would create the heteroclinic cycle. But they proved that motivated by Yuri Lyubich asked from Mizurevich to prove this theorem in early 2009 in some conference. Then Mizurevich, he said that he took the problem and he proved it for these cases. Yes, I got all these.
Light set, you mean non-countable,
Yes.
Continual light set, yes? Measurable.
Yes, so yes, if you have removed, like it's dense set, uncountable set. It's dense, uncountable. It has house of dimension more than one.
Okay.
O'tgan aka javob berdim savolingizga. Savol so'ramoqchi edingiz o'tgan aka. Rahmat, katta rahmat. E'tiborlaringiz uchun katta rahmat. Sog' bo'ling. Katta rahmat.
If the amina is not here, we may stop now for the dinner. We will complete after the session in 2 o'clock. Okay. Bekle devam etten Allah bitti. Sana selamlar. Kırmızı yapın.
Can you listen me?
Yeah, very good.
Yes. Okay. Thank you.
So we started for the
Bye.
Hello, Professor.
Hello. How are you?
Hi. Your talk 3:30. Yes.
Yes.
After 3 o'clock.
Okay. Can you listen me finally?
Yes.
Okay. How are you?
Fine. Now, yesterday I was in this room, but today I participated
in Samarkand?
with online. Yes, online.
Okay. Very nice meeting. I enjoy it very much.
Good morning, good afternoon, Professor Velasco. How are you?
Fine. Very happy to be here.
Yes,
I
thanks so much.
congratulate you by
Thanks so much.
this meeting.
Yes, I was reading your paper on this Markov, nonlinear Markov, like cubic matrices and the product. I like it very much, your results, your paper, introducing various kind of multiplication and studying the dynamics generated by these multiplications. And one of the things I'm also doing it, I like it very much. It was this great opportunity to meet you in a person. Thanks so much. It was very nice to meet you.
Thanks to you. I hope a very strong collaboration in the close future with colleagues from Uzbekistan. I am very happy working
Thanks
with
so much
them.
for joining and giving talk here. We look forward to attend your talk. Thanks so much. Enjoy your day.
Thank you. Thank you.